This video is about projectile motion. We will begin by discussing basic projectile motion concepts, and then look at an example involving projectile motion. Let's begin with the basics. A common situation in which projectile motion arises is when an object is fired from the ground at an angle to the horizontal. Such a situation looks like this. In most projectile motion questions, we will assume that air resistance is negligible, so let's make this assumption here. Since air resistance is negligible, the path of the object will be a parabola. So the path looks like this. Let's assume that the initial velocity of the object is v. v is a vector. Earlier we have learned that vectors can be resolved into a horizontal and a vertical component. Let's resolve v into two components. I will name the horizontal component vx and the vertical component vy. Let's not worry about the magnitude of these vectors for now. We will come to them later. As the next step, let's examine the velocity of the object at 4 other points along this parabola. At each of these points, the velocity vector is tangent to the parabola and looks like this. Let's resolve each of these vectors into a horizontal and a vertical component. Note that we did not have to resolve the velocity vector at the maximum point of the parabola, because here the velocity vector is horizontal. Examining the diagram, we can see that the horizontal component, so the light blue vector, remains the same, while the vertical component, so the red vector, changes throughout the object's motion. Between the starting point and the maximum height, it is pointing upwards and its magnitude is decreasing. At the maximum point, it becomes 0. Then throughout the second part of the path, it is pointing downwards and its magnitude is increasing. We have arrived to probably the most important concept in projectile motion. It is that the horizontal and the vertical components of the motion are completely independent of each other. Since the horizontal component remains the same, horizontally the object moves at constant speed. Therefore, when you are working with this component of the motion, you should use the equation v is equal to s over t, where v is velocity, s is distance traveled, and t is time. Based on what we have learned in an earlier video about resolving vectors, the initial horizontal velocity of the object, which in our diagram is denoted with vx, is equal to v times cosine theta. Here, v is the magnitude of the object's initial velocity, and theta is the angle that this initial velocity vector makes with the horizontal. The vertical component resembles the motion of an object thrown vertically upwards. Such an object has an initial vertical upwards velocity, it slows down as it's moving upwards, reaches a maximum height where it stops for a moment, and then it falls back towards the ground. We have discussed this type of motion in a previous video and concluded that the object has constant downwards acceleration due to gravity. In other words, its acceleration is the gravitational acceleration, which is denoted by lowercase g, and which I wrote here as negative 9.81 meters per second squared, using a negative sign to indicate that the direction of this acceleration is downwards. Because of this constant acceleration, when you are working with the vertical component of projectile motion, you should use the Suvat equations. We have covered how to use these equations in a previous video. Using vector resolution, the initial vertical velocity, or vy, is equal to v sine theta. A final key point to mention here is that throughout the entire motion of the object, the only force acting on it is the gravitational force. Intuitively, it might seem that there is also a horizontal force acting on the object, since the object is also moving horizontally, but remember that the horizontal component of the velocity is constant, and since constant velocity means no acceleration, there cannot be a horizontal force acting on the object. Let's move on to an example. We will examine the horizontal and the vertical motion of the object separately. Splitting the motion into these two components is usually a logical first step when working with projectile motion. Horizontally, the object moves at constant velocity, and vertically it has constant acceleration, the gravitational acceleration. For the horizontal constant velocity, we will use the equation v is equal to s over t, so our variables are sx, the horizontal distance traveled, vx, the horizontal speed, and t, time. Since vertically we have constant acceleration, we will use the Suvat equations. So here the variables are sy, the vertical distance traveled, uy, the initial vertical velocity, vy, the final vertical velocity, a, the acceleration, and t, time. Let's see which of these variables are given in the question. We know that the initial speed is 20 meters per second, and that the velocity vector initially makes an angle of 30 degrees with the ground. Using vector resolution, which we mentioned earlier in this video, Vx, the horizontal component of the initial velocity, is equal to 20 times cosine 30 degrees, which is about 17.3 meters per second. Uy, the vertical component of the initial velocity, is 20 times sine 30 degrees, and this is 10 meters per second. Vertically, the acceleration is the gravitational acceleration, and since it is pointing downwards, I will take it to be negative 9.81 meters per second squared. Just a quick reminder that you can find this value in your data booklet. It feels a bit like we are stuck here, because no more information is given in the question directly, so let's see another key idea that will help us move on. What happens vertically with the object is that it moves upwards, reaches its maximum height, and then falls back to the ground. To be able to work further, we should focus either on the upward or the downward journey of the object. Since we have the initial vertical velocity, which is pointing upwards, I will focus on the upwards journey of the object until the moment when it reaches its maximum height. Let's now go back to our variables for vertical motion. Sy is the distance traveled, in other words, the maximum height reached by the object, and this is one of the variables that we're looking for. Vy is now the final velocity of the object at the end of its upward journey, in other words, at the moment when it reaches its maximum height. Since at this point the object stops for a moment, Vy is 0. We don't know anything about the time, but I will rename it here Tu, or T upwards, so that we don't confuse it with the total time that the object spends in the air. This will be another variable that we will look for. Let's start by finding Sy, the maximum height reached by the object. Next, we need to choose a Suvat equation. Since we have u, v, a, and we are looking for s, we will use this equation. Substituting gives us 0 squared is equal to 10 squared plus 2 times negative 9.81 times s. Working further and rearranging, we get 19.62s is equal to 100. So for s, we get approximately 5.1 meters. So this is the maximum height reached by the object. Next, let's find the time it takes for the object to reach this maximum height. And since now we have s, u, v, and a, we can use any of the Suvat equations that includes t to find the time. I will use this equation. Substituting gives us 0 is equal to 10 plus negative 9.81 times tu. After rearranging and dividing, we get approximately 1.02 seconds for tu. This is the time taken by the object to reach its maximum height. Since the motion of the object is symmetrical in the sense that it takes the same amount of time for the object to reach its maximum height and to fall back to the ground, the total time, tt, will be 2 times tu, so approximately 2.04 seconds. let's move on and talk about another important key point related to projectile motion. This point is logical and straightforward. However, people tend to forget about it, and as a result, they struggle to make a connection between the vertical and the horizontal motion. The key point is that the time for the horizontal motion is the same as the time for the vertical motion. This means that since we found the time for the vertical motion, we have also found the time for the horizontal motion, which is therefore 2.04 seconds. From this, we can easily find Sx, the horizontal distance traveled, by rearranging the equation v is equal to s over t. So for Sx, we get v times t, 17.3 multiplied by 2.04, and this is approximately 35.3 meters. So this is the horizontal distance traveled by the object. Let's summarize what we have learned in this video. We started by looking at a typical situation that involves projectile motion, which occurs when an object is fired at an angle theta to the horizontal and air resistance is negligible, so that the path of the object is a parabola. We drew a diagram of this path, saw that the velocity vector is tangent to this parabola at every point and can be resolved into a horizontal and vertical component. We discovered that the horizontal and the vertical components of the motion are completely independent of each other. The horizontal motion of the object happens at constant speed, so when working with this component, we can use the equation v is equal to s over t, where v is speed or velocity, s is distance traveled or displacement, and t is time. We also mentioned that by using vector resolution, we can find the magnitude of the initial horizontal velocity, Vx, which is equal to v cosine theta, where v is the initial velocity of the object. We added that the vertical motion of the object resembles the motion of an object thrown vertically upwards, which means that there is a constant downwards acceleration, the gravitational acceleration, that has a letter symbol of lowercase g, and the magnitude of 9.81 meters per second squared, which here I express with a negative sign to show that its direction is downwards. Because of this constant or uniform acceleration, we can use the Suvat equations when working with the vertical component, and again using vector resolution, we can find the vertical component of the velocity, Vy, which is equal to v sine theta. We also deduced that the only force acting on the object is the gravitational force, and through an example, we saw two more key points about projectile motion. The first is that when we are working with the vertical component of the motion, we should focus either on the upward or the downward portion of the motion. And the second, which is logical and straightforward, but people tend to forget about it, is that the time for horizontal motion is the same as the time for the entire vertical motion, which is composed of the upward and the downward portion. This wraps up our discussion of projectile motion and completes the final video of subtopic 2.1. Note that in the IB Physics Guide, fluid resistance and terminal speed are part of subtopic 2.1. However, since it's easier to explain these concepts using free body diagrams, you will find the fluid resistance and terminal speed video in subtopic 2.2.